Hello everyone. We are looking into the gravity methods of subsurface exploration. Right. If you recall, in the previous lectures, we had seen some fundamental aspects of Earth's gravitation. Especially, we focused on Newton's law of gravitation. Then we had seen what are the reasons for large scale and small scale variations in the acceleration due to gravity measured at the surface of the Earth. Then we had a look into different gravimeters, different types of gravimeters. Toward the end of the previous lecture, we had seen how the gravimeters are calibrated before carrying out the work at the field. And this is the slide we had seen toward the end of the previous lecture, how we carry out the survey in the field. Usually, gravity survey is carried out in the grid pattern. The most important thing is surveying, especially leveling and surveying, which is very easy nowadays because of the differential global positioning system which we have today, and it is necessary to have the precise location in especially the latitude, because we have seen already from equator to the pole the Earth's gravity varies, which is the large scale variation, which we need to eliminate to understand the variation in the gravity value due to the density of rocks, due to the changes in the density of rocks. Similarly, elevation is also necessary. That is what is being done here. After that, we carry out the measurement using the gravimeter. Using gravimeter in the field will not take much of our time, right? Maximum 2-3 minutes is sufficient, right? To course leveling and then take the reading in the gravimeter, right? After that, several corrections need to be applied. After the corrections are applied, then the data is ready for interpretation. Interpretation is done either in qualitative way or in a quantitative way, right? So, that is what we are going to see in this lecture. So, before going into this, next aspect is corrections, right? We had seen up to this in the previous lecture, right? Next is the corrections. While doing the survey in the field, I said grid pattern, the survey can be for different purposes, right? When you want to do on a large scale, very regional level surveys, much more than regional level survey, it is possible to carry out the gravitational survey from air. That means gravimeter can be taken, can be airborne gravimeters can be used. So, you can carry out the survey over a very large area. Another advantage of gravity survey is we can also do the same from the ships, right? We can carry out survey on the ocean to understand the variation in the rocks beneath the ocean floor, right? Now, let us focus more on the corrections. Before looking into corrections, what are this, right? Either the survey can be carried out sometimes called as microgravity survey. That means in microgravity survey, our interest is to understand small objects below the surface of the earth, maybe something like this, right? A small cavity or buried objects, right? And especially we are able to understand the presence of bunkers or caves in limestones can be understood from gravity survey, because over the region where we have caves, right, this is the surface of the earth. Suppose if there is a big cave here, when you carry out gravity profile from on the ground surface, gravity values will be little lower just above this cavity, right? Gravity value is lower here, right, at this place, right? So, this kind of survey to identify smaller objects are known as microgravity survey. Then the next level is known as small scale survey, in which we try to understand a variation in the rock types or variation in the thickness of the layers, right, over a small region, right. That is known as small scale gravitational survey, right. This is also possible for exploring minerals, right. In exploring minerals too, we can do small scale survey, small scale gravitational survey. Then in medium scale, we try to understand relatively large structures, right, especially structures running to several tens of kilometers, right. Such as a big anticline. This is the ground surface. Beneath the surface, you may have the formations in the form of an anticline, that is, it is like a curve, right. So, this is known as an anticlinal structure. Such anticlines can be understood from medium scale survey. Then we have a very large scale survey, that means countrywide, over the country of India or along the east coast or west coast of India. We may do a survey to understand a large scale variation in the gravitational acceleration due to gravity, right. For example, when you fly from, let us say, from Kolkata, I'm just roughly drawing the map of India. Kolkata is here, and let us say Thiruvananthapuram is here, right. When you fly from Kolkata to Thiruvananthapuram along the coast of East India, right, you assume that we are making the measurement of gravitational pull along this line, right, along this line from Calcutta to the southernmost tip, maybe Kanyakumari. We are flying and carrying out the measurement of variation in the acceleration due to gravity. Acceleration acceleration due to gravity will be very comparatively lesser wherever we have thick sediments, isn't it? So, very easily we will be able to decipher the thicknesses of the river basins, right. That is what we look for in oil exploration. Such gravitational survey are known as large scale survey, right. And also over the entire ocean or over the entire world, we carry out gravitational survey to understand how the thickness of the Earth's crust thickness in continents will be about 35 kilometers. Is the thickness increasing? In several regions of the world, thickness of the crust is thinning, right. That means it is thinning is taking place because of the theory due to the movement of plates. They can be also studied using large scale variation in the acceleration due to gravity. These are the 4 different type of surveys which we carry out, that depend on what? It depend on the objective of our study, right. Now, after having seen this, as I told you, let us move on to the next thing, that is what we had seen in this slide, right. We will have a look into what are all the corrections that are need to be given to the gravity data which we have collected from the field work. Broadly, the correction that needs to be given are also called as reduction of data, right. Correction or reduction mean the same in gravitational survey, right. Here in this case, what we are going to see is how the gravity data which we have obtained can be corrected or reduced, right. That means before using the data which we have collected from the field, the data need to be reduced, right. What is that? Reduction is the process of removing the effects of local features, which mask the true gravity value of a given location, right. So, this process is known as removing the effect. As an example, right now I can tell you what do I mean by local features. Imagine this is the surface of the earth on which we are doing the gravitational survey. Imagine this is our station 1, station 2, station 3, right. Imagine station 4. Now, by looking at this diagram, which is nothing but a cross section of a ground surface showing the locations of gravity stations, right. And here we can see location number 1 is little bit higher than location number 2, isn't it? So, the elevation difference between 1 and 2 itself will cause some variation in the acceleration due to gravity value measured at location 1 and location 2, isn't it? So, we are going to remove that. This process of removal is known as reduction of data. That means what we are going to do, either you will take the station to the same level of location 1 or reduce the elevation of location 1 to the level of location 2. Is that clear? So, this process is known as gravity reduction. We are going to see that in little more detail soon, right? Then what is the advantage of doing the reduction? This brings the measurements to a common spherical surface, which we call it as geoid, right? So, there were so much of undulations on the surface of the earth, which we are removing, right? So, by removing, what we are achieving, this area is converted into a kind of a flat terrain. This is location 1, 2, 3 and location 4. By carrying out correction, we are bringing all the stations at the same level, right? So, that is what I have written here. So, this brings the measurement to a common imaginary spherical surface known as geoid. Now, we have carried out the corrections, right? After carrying out the corrections, now let us take the same example. After carrying out all the corrections, if the value of acceleration due to gravity is different between these stations, station 1, 2, 3, 4, what does it indicate? We have carried out all the corrections. What do I mean by correction? That means we have reduced the data to overcome all the effects of changes in the latitude, changes in elevation, right, and additional thickness. We are going to see one after another. So, we have incorporated all the corrections. Even after carrying out the corrections, the values measured at 1, 2, 3 and 4, they are different, right? What does it indicate? That indicates some real anomaly, right? After carrying out the corrections, right, still if there are differences in the gravity value, that indicates some anomalous conditions beneath the surface of the earth. That is the purpose of gravity data reduction, right? You will understand it little more better as we progress. There are number of corrections that are given to the gravity data. However, for simplicity, we are going to take into account of a few major corrections or only we are going to consider. In fact, if you carry out this correction, that itself is more than sufficient, right? So, what are all the corrections which we are going to see? We are going to see first is the latitude correction, right? We had seen right at the beginning, earth is not a sphere, but it is a sphenoid, right? That means the radius of the earth is from the center to the equator is nearly 23 kilometers larger than the radius between the center to the pole, right? Compared to, if you consider this as x and this as y, y is 23 kilometers larger, right? This itself affects the gravity value which we measure at the surface. That means, if you measure the gravity here at the equator, gravity value is expected to be slightly lower. Why? As per the Newton's law, force of attraction of the mass which is kept here by the mass of the earth is related to the distance between them. Now, the distance is 23 kilometers more. If you keep the same mass here, it will experience higher gravity, isn't it? This have to be corrected. This difference have to be corrected. That is what is known as latitude correction. Then free air correction. We are in free air correction, right? Some station may be, let us assume, right, this is the surface of the earth, right? This is the ground surface on which we are carrying out the survey, right? This is station 1, station 2, station 3. They are all at different elevations. So, this, let us imagine this is the center of the earth, So, from the center of the earth, now station 1 is little bit away compared to station 2. Similarly, station 2 and 1 are much more away from station 3, isn't it? This has to be corrected for. That is what is known as free air correction. In free air correction, we try to overcome this issue. Then we are going to, I will skip this sentence, right? Next is Boger correction. Here, the Boger correction takes into account of additional mass. Now, let us see, compared to station 3, the value measured at station 1 takes into account of additional mass of material present, as I am drawing here. Whereas, this much of additional mass is not present at station 3. This we account for. That is what is known as Boger correction. Then lastly, terrain correction. In terrain correction, we take into account of the impact of hills and valleys adjacent to our gravity station, right. These are all the corrections which we are going to see, right. For your understanding, I have written a small description here. However, I have not explained that here, because we are going to see each and every one of them in detail in the forthcoming slides. First, let us take up latitude correction, right. This is the first correction we are going to take up. I had already explained to you, gravity values are varying because of the change in the latitude of the earth. From the equator to the pole, the earth's gravity, acceleration due to gravity is increasing. We have used the formula which is known as International Gravity Formula during our physics laboratory, in which we would have used a simple pendulum to determine the acceleration due to gravity of the location at which you have carried out this simple pendulum experiment, right. Instead of that, if you know the latitude of your location, then we can determine the acceleration due to gravity over there using the International Gravity Formula. The International Gravity Formula reads like this. The only variable here is this, that is nothing but latitude. Right. So, if you substitute the latitude, the formula gives the acceleration due to gravity, which will be about somewhere around 978. Okay. So, we are able to determine the actual expected gravity at different latitude on the surface of the earth, right. So, usually horizontal gravity gradient is determined at the base station from the latitude, right. What we are going to determine is what is the actual expected gravity at the base station. What is base station, right? When you are doing the survey in the study, suppose if this is the boundary of your study site, as we had seen, usually we carry out the gravity measurements in grid pattern, right. Among several stations, we choose one station and call it as base station. What is the criteria to choose a base station? Generally, base stations are stations which are easily approachable, right, preferably at the center of the study area. For example, here there are so many stations we have identified. Let us say this I am going to choose as base station. What is the criteria? Since I don't have much of a detail, this is a study site, I have chosen this is the more or less at the center of our site. So, I have chosen this, right. But we need to also consider the site condition. Is it easily accessible? Is there a roadway nearer to that, right? It should not be in the midst of a forest. Why? Base station has to be frequently visited by us. Over there, we are going to collect the readings at different times, especially to understand diurnal variation in the acceleration due to gravity. We are going to see that too little later, right? So, as of now, let us understand a base station is a station which is chosen among our gravity stations which is easily approachable. That means we are taking into consideration of the logistics. Is there a roadway, so that you can frequently you need to visit the base station at frequent intervals, maybe every half an hour or 1 hour, to repeat the readings. So, for that base station, we determine the acceleration due to gravity value based on its latitude. Okay. Then what we are going to do after that is, we know gravity value increases toward the pole. Let us assume for this map, this is north, and let us imagine latitude of this line is 13 degrees north, which means this region is in which hemisphere? In northern hemisphere. In northern hemisphere. In the northern hemisphere, within our steady state, gravity value is expected to increase from south to north. Why? Because in the south, we have the equator. At the equator, Earth's radius is 23 kilometers more. Because the radius is more, the gravity value which we measure there is expected to be marginally less than the value which we will measure at the poles. Okay. Same effect will also happen in our steady state, right, which is more or less like a square as I have drawn. So, gravity value in this station, right, let us say this is station number 21, right, I am just writing. In station number 21 is expected to be much, let us say this is station number 6. What is the expected difference in the acceleration due to gravity between 6 and 21? Location number 6 is further north of location number 21. This steady site is in the northern hemisphere. So, gravity value at 6, station number 6 is expected to be more than station 21, isn't it? The station number 21 value is expected to be little less than the station number 6. Why? Because 21 station is slightly far from the center of the earth than the location number 6, right. So, that is what we are going to correct. So, latitude correction is more negative towards the poles, right. That means what we are going to do. So, here the value which we have measured is expected to be more. We will correct that by reducing the gravity value which we have measured. That is what is known as latitude correction. How do you carry out the latitude correction? By substituting the latitude of this location, right. Let us say this is 12 degree, right, 57 minutes. Let us assume the location, this is the latitude of location 21. Latitude of location number 6 is 13 degrees 10 minutes, right, 0 seconds. What we will do? We will substitute this value to the gravity formula, substitute this gravity value to this formula. We will have two g values. We know the difference between these two, right. You get, let us say here for station number 21, when you use the gravity formula, the value which you got is 978.32. For station number 6, when you use the formula, the value you should have got should be slightly more than this, isn't it? let us say we got 978.812, right. Now we know the difference between these two, right. That difference will be subtracted from the value we have got at station number 6. This is what is latitude correction, right. Approximately the latitude correction at 51 degree north is about 9 gravity unit per kilometer approximately, right. So, this is what is known as latitude correction. What we are achieving by carrying out latitude correction? We have achieved, right, what is known as a highest level of accuracy is necessary. How can you give highest, how can you achieve highest level of accuracy in gravity survey? Only by precisely knowing the locations of all the stations, right, at least with an accuracy of plus or minus 10 meters, especially along north-south direction. East-west, no problem with regard to latitude, right, because they are all at the same latitude. So, the effect of the radius of the earth is not going to be there at all, isn't it? So, at least to have 10 plus or minus 10 meters is necessary in order to achieve an accuracy of this much in gravity correction. Imagine that we have corrected all the readings we have collected at the field. What we have done? Can you tell me what we have done? We have eliminated the effect of latitude, isn't it? So, practically what we have done is, though these stations are located at different latitudes, for example, let us take location 2 and location 6. One was at 12 degree 57 minutes, another one was 13 degree 10 minutes. After carrying out the correction, what we have done? We have brought them to the same latitude, right. Suppose if I had reduced the value here, what I have done? I have brought this location, though it is located at 13 degree 10 minutes, I have converted that into station 6 is also located at 12 degree 57 minutes. Is it clear to you? Right. That means, very simply, we have eliminated the effect of latitude. We have converted all the values which we have obtained during the after the gravity investigation, gravity survey, in such a way all the stations are at the same latitude. That is what is latitude correction, right. Now, let us pass on to the next correction, which is known as free air correction. In free air correction, right, what is happening is, we try to correct for reduction in gravity with height above the geoid. Geoid is a spherical earth, right. Let us say this is one gravity station. This is another gravity station. This is location number 1, location number 2. Okay. Now, what we have done? We have made one measurement at location 1. Next reading was made at location number 2. What is expected now? In which location gravity value is expected to be more? Why? Can you answer me? In station number 1, gravity value is expected to be slightly higher than the location number 2. Acceleration due to gravity in station number 1 is more because station number 1 is little bit closer to the center of the earth, whereas location number 2 is little bit away from the center of the earth. What? How much? That is this. This is the h. Let us say h is 10 meters. If you assume, then station number 2 is 10 meter away from the center of the earth compared to station number 1. This effect we are going to eliminate. This is what is known as free air correction. So, free air correction is the difference between the gravity measured at sea level and at an elevation of h, right. So, here station number 1 was at the location of sea level, station number 2 was at a different level. Now, we are going to eliminate the elevation difference. How? By assuming there was no rock present between these two stations. That assumption is made here. Okay, that means what we are able to achieve? We are able to achieve the elevation difference between them is removed, right. This is what is known as free air correction. So, corrections of elevation with respect to elevation we had already seen, where we had seen when we had a look into calibration of gravimeter. What was one method of calibration? How we can check the gravimeter which we are using is functioning well or not. There also we had seen by taking measurement at different altitudes, right. There itself we had seen the gravity value will vary by point. I will go back and show you the gravity calibration we had seen previously, right. So, in calibration we had seen one of the methods of estimating the carrying out calibration is making measurements at different altitudes. So, it should vary by this much for every meter difference. So, the same principle we make use of here to carry out the correction with to overcome the problem of elevation, which we call it as free air correction. So, this will be about 0.3086 milligauss per meter, or it is 3.038 gravity unit per meter. Okay. So, this correction we are making. Now, imagine this station number 2 is 10 meter above. Now, we want to make this as a reference. That means what? We are going to bring station 2 to the mean sea level. In order to do that, what we have to do? 10 meter multiplied by 0.3086, right. We will get some value. What value we will get? 3 equivalent to 3.086 milligauss, isn't it? What does it mean? When the gravity station was here, the value of gravity which we have measured actually have to be will be less than, or it will be slightly less, isn't it? How much it will be less? It is expected to be less by 3.086, because it was at an elevation of 10 meter compared to higher elevation, at an higher elevation compared to station number 1. So, what we will do? The reading which we have obtained for station number 2 will be reduced by 3.086. By doing so, what we have done? Though station number 2 is at 10 meter above, we brought that station to the same level as that of location 1. I am sure it is clear to you now. This is what is known as free air correction. Okay. Next is Boger correction. So, before going into Boger correction, right, suppose I have written something, right. Let us imagine station number 3 is, this is station number 3. This is 2 meter below the reference station. What would have happened here? The reading which we have measured would have been more, isn't it? Right. So, here the value which we have got would have been less. So, we are adding 3.086, right. Now, here the value which we have measured would have been slightly higher because it is much closer. Hence, we have to add, how much we have to add? 2 times of 0.3086 at approximately, let us say 0.6. For the value which we have measured, we will add 0.6. For this value, you will subtract minus 3.086. So that this value is brought down here. When you add, this station is brought to the same level. This is what is known as free air correction.